Hello, we're Team 11. My name is Mario Carvajal.
Jorge Silva.
And Juan Bernabeu.
And today we're going to be talking about failure theories for static loading. Okay, so let's start off by defining what a static load is. So a static load is a stationary force or couple that's applied to a member. It must not change in magnitude, direction, or point of application to be static. This load can create an axial, shear, bending, or torsional stress inside the material. So now, let's define what failure is. So failure means that the part of interest is either broken into many pieces, has become permanently distorted, or its function has been compromised in any type of way. So as an example here, we have a screw that is broken in half due to the stresses that it was under during operation. So ideally, an engineer, when designing a part, would like to come up with a prototype of the exact part that they're using and test it in the exact same conditions that it would be in during operation. So for example, if the part was machined and it's supposed to be machined and heat tempered at a certain temperature and have a certain surface finish, the prototype would have the same exact one, and it will be under the same exact loads that would be in during operation. This way, it will give you the most accurate readings for when the part will fail. However, this isn't very practical. This will be very expensive, time-consuming, and most of the time it's not the correct way to go. So what we use instead is failure theories. So failure theories use basic information about a material, such as elastic modulus, and then also they use the load that the part will be on, so we can get a pretty reliable prediction for when the part will fail. So materials are generally classified into two different groups. There are ductile materials and brittle materials. Ductile materials, when they are loaded, typically they will start to deform plastically before failure. And this process is called necking. So an example of that is seen here in B, where as the rod is put into tension, the diameter in the middle starts to reduce and soon will break. And here's a real-life example of that same rod starting to do the necking process. Now, brittle materials do not undergo this process. They will not begin to plastically deform, so when they are loaded, they stay within the linear elastic region of the stress-strain curve. So before any plastic deformation can occur, it will just snap, like here in part A. And an example is right here, one of the rods in the tension test. So since these two materials act very differently when failure occurs, we generally have two categories for failure theories. There are those for ductile materials, and the ones we're going to cover today are maximum shear stress, distortion energy, and ductile Coulomb Moore. And then for brittle materials, we're going to talk about maximum normal stress, brittle Coulomb Moore, and modified Moore theory. So before we start talking about any of the failure theories, let's talk about the conventions used. So in all the failure theory calculations, we use the principal stresses. So in our figure here, this is a 2D projection of an element, and it shows all the stresses that could be happening in that 2D plane. So there are axial stresses in the x direction and the y direction, and then there are shear stresses that point in opposite directions on the edge of the element. So from these, we can calculate the principal stresses. Now what principal stresses are, there's one for each of the directions. So in our 2D plane, there are two principal stresses. There's one in the x direction and one in the y direction. Now it is important to realize that there is a third direction, since these stresses happen in 3D. So third direction would be out of the screen. So once we calculate these three principal stresses, another convention is to reorder them in ascending order. That's going to be seen here in our inequality. So now let's talk about what maximum shear stress theory is. So maximum shear stress theory predicts that whenever the shear stress inside of the part exceeds the maximum shear stress that the material can withstand, failure will occur. Okay. Now, the idea behind this is that when a sample of a material is put under tension, like in the tensile test rods that I showed you in the last slide, when necking occurs, inside that necking point, there's these things called slip lines that are the signs of the plastic deformation. These slip lines occur at a 45-degree angle to the tension axis. Okay, and it also so happens that shear stress is a maximum at a 45-degree angle to the tension axis. So the hypothesis is that failure is the result of this shear stress. Okay. So from this equation down here, the maximum shear stress is equal to the actual stress and tension divided by 2. Okay. So now applying that to our failure theory, it says here that the maximum shear stress that the material can withstand, or the part that can withstand, is equal to the yield strength of the material divided by 2n. Now that n there is a factor of safety, and factor of safety is an arbitrary number greater than 1 that engineers select to stay away from the actual yield point. It's kind of like a buffer so you don't get too close to yield. Now here we can see the failure envelope for maximum shear stress. If inside of this shape, in the blue area, you're safe and there's no failure will not occur. Okay. Once you get to the black edge there, that is where the predicted failure will occur. Okay. So this x-axis is one principal stress direction, and the y-axis is another principal stress direction. So this is for 2D. And as we will see later in the next slide, this failure theory is relatively conservative compared to other failure theories.
Okay, hi, my name is Juan Bernabeu. I'm going to talk about the distortional energy theory. So the distortional energy theory predicts that failure occurs when the distortion strain energy in any element surpasses the distortion strain energy required for yield in tension or compression for the material. So where does this come from? Basically, the idea behind the theory became popular when the experiments of materials were loaded underwater, so hydrostatically, where all the pressure is the same in each phase, and we have equal principal stresses. So they found out that they were able to surpass the yield strength of the material loaded in one direction, which means that failure is not a simple measure with intention or compression, but instead is related to the angular distortion inside the material. Basically, the strain energy is given by the equation here, which relates the ultimate the yield strength with the safety factor n and the principal stresses. We see here that the equations we have to first order the principal stresses as sigma 1, sigma 2, and sigma 3, and have them put them in the equation as shown here. So basically, the distortional energy theory is a very accurate predictor of the failure. For this reason, it is the most widely used failure theory of all ductile materials. The yield envelope, like we see here, is inside, so the von Mises, which is the distortion energy, is outside of the maximum shear energy. So basically, the envelope involves the maximum shear stress envelope, and it's clear that this is why we use the distortion energy the most, because it's the most conservative, but it's really accurate. Next, we're going to talk about the ductile Coulomb-Moore or DCM theory. So the yield strength of a material in tension is not always the same as in compression. Actually, some materials can withstand a very large compressive load, but when you tested to the tensile load, it snaps quick. So the ductile Coulomb-Moore takes into account this fact, that the compression can be applied more force than in tension. So this theory was constructed by conducting 3 yield tests on the material in compression, tension, and shear. Using the results, a circle is constructed like here. 1, 2, and 3. And so we can see that the failure envelope is a line tangent to all those circles, the 3 circles on top and the bottom, like we see here in this figure. So the equation depends on the yield strength for the material in tension and in compression, like we see here. Tension, compression. And it's also related to the safety factor, like every other theory. So the yield envelope clearly shows that the material is created so that it can sustain much higher loads in compression than in tension, like we see here. So next is the maximum normal stress theory, or MNS theory. This theory was one of the first failure theories devised for brittle materials. It's called the maximum normal stress, and it states that the material will fail in any of the principal stresses if any of the principal stresses surpasses the yield strength of the material either in tension or compression. The failure envelope is a square, and due to the empirical evidence that we have, we know that the maximum normal stress theory does a very, very poor job in predicting failure in the second and fourth quadrants. Therefore, towards the corners, the material fails with still inside the failure envelope. So it does a very, very poor job, and it's almost never used.
Hello, my name is Jorge Silva, and I will go over brittle Coulomb-Moore and modified Moore as failure theories. The brittle Coulomb-Moore and modified Moore theories are both derived using the same concept as the ductile Coulomb-Moore theory for ductile materials, but now using empirical data from tests on the brittle material. The figure shows the 3 failure envelopes for the brittle materials together and some experimental values for yield. We have the max normal, the modified Moore, and the Coulomb-Moore. The three theories share the same first and third quadrants, but they are different in the second and fourth. The brittle Coulomb-Moore theory pulls back the failure envelope away from the maximum normal stress and under the experimental yield values. The modified Moore theory tries to adjust the line to closer fit the experimental values. Next, we go over how to select the appropriate failure theory. When selecting a failure theory, many elements on the design process need to be taken into consideration, like time, accuracy of the prediction, and how much money we are willing to spend on the test. Here we have a simple flowchart form that we can use to set when selecting the appropriate failure theory. We have 2 behaviors on a piece or material or element when we take into consideration which way we need to go. We have the brittle behavior and the ductile behavior. When we go into the brittle behavior, we need to take into consideration that the allowable deformation that a piece is willing to take is less than 0.05. Then we need to go over how conservative the failure theory that we're going to apply needs to be. If it doesn't need to be really conservative, we can go over to the modified Moore, and if it needs to be conservative, we can go over to the brittle Coulomb-Moore. Then when we go over to the ductile behavior, we need to take into consideration if the tensile and the compressive forces are equal or opposite. If they are not, we can go over to the ductile Coulomb-Moore. And if they are, we then need to take into consideration how conservative we need this to be. If it doesn't need to be really conservative, we can go over to distortion energy. And if it needs to be really conservative, we can go over to the maximum shear stress failure theory. To conclude, we can say that engineers, when facing tasks, problems, or jobs, they have many tools at their disposal. And one of these tools are the failure theories. They are very important when it comes to design. When it comes to a design, This tool helps an engineer to avoid wasting time and money or even resources of a company in a project when trying to modify a design. This is thanks to being able to predict accurately how a piece is going to behave and when it's going to fail. When deciding what type of theories need to be applied in what case, in what conditions, we need to study the case and then select what theories applicable in the situation and what the outcome will be. Thank you.